Good evening, everyone. Last class, we have discussed questions from some basic concepts of chemistry, right? Today, we'll be discussing questions from atomic structure or quantum mechanical model of an atom. Okay. So, what are all the subtopics you guys studied in atomic structure? Is my screen visible? Okay. So, what are all the subtopics you guys studied in atomic? Tatvatika, Divya.
Yes, ma'am.
You just tell me any topic which you studied in atomic structure. Any topic, any subtopic.
Ma'am, Heisenberg uncertainty principle,
Yes.
Pauli's exclusive principle, Hund's rule,
Okay.
work principle,
Okay.
the structure of electron, proton, and neutron.
Okay, fine. Poontamizharasi,
Ma'am,
what are all the topics you studied in atomic structure, Kanna?
time independence Schrodinger equations,
Okay.
Hund's rule,
Okay, fine.
de
Okay.
Broglie equation.
De Broglie's wavelength. Yes, right. Okay, very good. Very good, Poontamizharasi and Tatvatika. Okay, fine. So, in this chapter, you would have studied about lot of atomic models proposed by different scientists in various time periods, right? You would have studied about John Dalton, J.J. Thomson, Rutherford, Bohr's model, and all that. In which Bohr's model is quite important because we can expect questions from Bohr's model. Basically, in Bohr's model, you have to know the formula to calculate the energy of the electron in an atom. And also, you have to know the formula to calculate the velocity of the electron. And also, you have to know the formula to calculate radius of the atom and all that. You guys are familiar with that formulas, right? To calculate energy, velocity, momentum, and all that. What is the formula to calculate the energy of an electron? Minus 13.6.
Z square by n square, ma'am.
Yes, Z square divided by n square electron volt. Here Z is the atomic number and n is the shell in which electron is present. And here the unit of energy is electron volt. But energy can also be expressed in terms of joules, calories, ergs, and all that, right? And definitely we have to know the conversion between all these units. So what is 1 electron volt? It is 1.6 into 10 power minus 19 joule. And what is 1 calories? It is 4.18 joule. And what is 1 joule? It is 10 power 7 ergs. You have to know all those conversions. Okay. So from this formula, we can calculate the energy of the electron. But this is for Bohr's model. Bohr's model is applicable only to hydrogen and hydrogen-like systems, right? What is hydrogen-like system? Hydrogen is fine. What is hydrogen-like system? The atom which contains only one electron or the chemical species which contain only one electron, right? So we know hydrogen. Hydrogen got only one electron. That is fine. How about helium? How many electron helium have? How many electrons will have? Basically 2, right? So Bohr's model is not applicable for helium atom, but this is applicable for helium ion, right? Bohr's model is not applicable for lithium, but lithium for lithium 2 plus we can apply Bohr's model because lithium 2 plus will have only one electron. So Bohr's model is applicable for hydrogen and hydrogen-like systems. Okay, and this is the formula to calculate the energy of the electron. And what is the formula to calculate the radius of the atom? Basically, what is radius? It is the distance between the center of the nucleus to the valency shell, right? What is valency shell? What is valency shell?
It is the outermost cell which takes
Right.
bonding.
Exactly. So, outermost shell is called valency shell. For example, this is the structure of atom and this is the nucleus. For example, this is first shell, this is second shell, this is third shell, and this is fourth one. Let us say this fourth shell is the outermost shell, then that is called as valency shell. Okay. So, distance between the center of the nucleus to the valency shell is the radius of the atom. And what is the formula to calculate the radius? It is 0.529 n square divided by Z angstrom. What is the value of angstrom? Angstrom is nothing but it is 10 power minus 10 meter, right? And also we have to know the formula to calculate the velocity of this electron. And to calculate velocity, formula is 2.19 into 10 power 6 Z by n meter per second. And also we have to know the formula to calculate angular momentum. What is the formula to calculate angular momentum? Mass into velocity into radius, MVR. And there is another formula to calculate angular momentum, which is NH by 2 pi. N is nothing but the shell in which electron is present. But what is H? What is H?
It is Planck's constant, ma'am.
What? Very good. What is the value of Planck's constant?
6.626 into 10 to the power minus 34 joule second.
Yes, 6.626 into 10 to the power of minus 34 joule seconds. And joules can also be expressed in terms of kilogram. So, how? Kilogram meter squared second power minus 2. So this unit can be substituted in terms of joule. So what will be the unit of Planck's constant then? 6.626 into 10 to the power of minus 34 kilogram meter squared second power minus 1, because 1 second inverse and 1 second will get cancelled out, right? That's it. So we have to know all these formulas which are related to Bohr's atomic model. After which you would have studied about quantum numbers and different types of quantum numbers and their physical significance, right? So what are all the quantum numbers you have studied? You have studied about 4 quantum numbers, right? What are they? Principal quantum number, azimuthal quantum number, then magnetic quantum number, spin quantum number, right? Basically, principal quantum number represents the principal quantum number represents what? It represents. Come again, Kana?
It represents number of orbitals, that is n.
Okay, basically that represents the shell or energy level. Okay, so n is the principal quantum number which we are giving to the shell or the energy level of the atom, and azimuthal quantum number is the quantum number which we are given to the subshell, which is S, P, D and all that. And magnetic quantum number is the number which we are giving to the orbitals, and spin quantum number is the number which we are giving to the electron. Will give the data about the size of the atom, and azimuthal quantum number will give the shape of the orbital. Magnetic quantum number will give the orientation of the orbital, and spin quantum number will give the spin of the electron. That's it, right? And you would have studied few formulas related to quantum numbers to calculate maximum number of orbitals, to calculate maximum number of subshells in a shell and all that. You guys are familiar with that, I guess, right? For example, how much orbitals are present in fifth shell? How much orbitals are present in fifth shell? Calculate and tell me how much orbitals are there in fifth shell. Basically, what is the formula to calculate number of orbitals in a given shell? Okay, let us calculate now. Okay, now I'm calculating manually, but I'll tell you the formula also. The shell, what I asked is fifth shell, right? So n is equal to 5. In fifth shell, how many subshells will be there? In fifth shell, how many subshells will be there? Okay, to make it simpler, first we'll see how much orbitals are there in second shell. Okay, after which we can calculate for fifth shell, because 5 is little bigger number. Maybe it may be difficult for you to calculate now. Now we'll calculate for second shell, and later we can calculate for fifth shell also. Okay, so let us take, I have second shell. Okay, in second shell, how many subshells will be there? Okay, write down the formula. Number of subshells in a given shell is, write down the formula. Number of subshells in a given shell, in bracket write it as n, which is equal to n. In first shell, there will be only one subshell. In second shell, there will be two subshells. In third shell, there will be three subshells. In fourth shell, there will be four subshells. Now tell me how many subshells are present in second shell. In first shell, there will be only one subshell. Okay. In second shell, there will be two subshells. Okay. In third shell, there will be three subshells. What I'm asking is, in second shell, how many subshells will be there? It is
two.
Right. It is 2. Okay. What are those two subshells? Basically, the number what I'm the number which represents subshell is azimuthal quantum number, right? So as you told, there are two subshells are present in second shell. First subshell's number is L is equal to 0, and second subshell's number is L is equal to 1. Okay. So in second shell, I have two subshells, one is 0 and 1. So L is equal to 0 can be represented as S, and L is equal to 1 can be represented as P. In S subshell, how many orbitals will be there? Only one, right? How to calculate number of orbitals in a given subshell? Write down the formula. Number of orbitals in a given subshell, in bracket write it as small l, which is equal to 2l plus 1. Okay. This formula will give you the number of orbitals in a given subshell. So here L is equal to 0. In the subshell, how many orbitals will be there? The formula is 2L plus 1. Here L is equal to 0. So 0 into 2 is 0. 0 plus 1 is 1. Only one orbital will be there. And in L is equal to 1 subshell, that is P subshell, how many orbitals will be there? L is equal to 1. So 2 into 1 is 2. 2 plus 1 is 3. So basically 3 orbitals will be there. So in second shell, totally how many orbitals I have? 1 plus 3, 4. Okay, as simple as that. Now we'll calculate for third shell. In third shell, how many subshells will be there?
5.
3. L is equal to 0, L is equal to 1, and L is equal to 2. According to this formula, now we'll calculate number of orbitals. Okay. In L is equal to 0, I'll be having only one orbital. In L is equal to 1, I'll be having 3 orbitals. And L is equal to 2, how many orbitals I'll be having?
5, ma'am.
Very good, it is 5. That's it. So how many total number of orbitals I have in third shell? 1, 2, 3, 4, 5, 6, 7, 8 and 9. Right. So if so there are 9 orbitals in third shell. So basically the formula to calculate number of orbitals in a given shell is n square. So in second shell, I have 4 orbitals. In third shell, I had 9 orbitals, right? So in fifth shell, how many orbitals I'll be having?
I'm 25.
Very good, that's it. So write on the formula, number of orbitals in a given shell is n square. That's it. Fine. So you have to know all these formulas. Okay. So we have seen this, these and this one. Okay. And also you have to know how to write the electronic configuration. Basically, what is electronic configuration? You have to know how to arrange the electrons in a given atom. So to arrange that, you have to know few principles like half-pass principle, Hund's rule and Pauli's exclusion principle, right? What is half-pass principle? What is half-pass principle? Whenever you are filling electron, you have to fill the electron from lower energy to higher energy, right? So that rule is called half-pass principle. For example, if you guys are provided with 4 orbitals, okay, among these 4 orbitals, you have to know which orbital got lower energy and which orbital got higher energy. How to find that? How to find which orbital got lower energy and other got higher energy? How to find that? Is there any formula to do that? There is a rule. There is a rule called N plus L rule. N plus L rule. Okay, I'll give you a few orbitals and please let me know what are all let me know the proper increasing or decreasing order of energies, okay? For example, I have 4D, 5P, 5F, and 6p orbitals. Okay, I have 4 different orbitals and I want you guys to arrange these orbitals in the order of decreasing energy. I want you guys to arrange these orbitals in decreasing energy. And what is the rule? We have to follow this N plus L rule. The orbital with lowest N plus L value will have lower energy. The orbital with higher N plus L value will have higher energy. If both orbitals had a same value of N plus L value, then check for the principal quantum number. If the principal quantum number is less, then that orbital will have lesser energy. You guys got my point? Okay, so let us calculate for 4D. Here, value of N is 4. And what is the value of azimuthal quantum number? Basically,
2.
Yes, very good. So L is equal to L value can be 0, 1, 2, 3, 4, etc. This 0 can be represented as S, P, D, F, G, H, I, J, K and all that. Okay, here this is D. So value of D is 2. So 4 plus 2 is 6, right? Okay. How about 5p? N value is 5 and L value is 1, right? So 5 plus 1 is again 6. And how about 5f? N value is 5 and how about f value? It is 3. So 5 plus 3 is 8. And how about 6p? What is the value of 6p?
7.
Yes. So 6, the value of N is 6 and value of P is 1. So 6 plus 1 is 7. I asked you to arrange these orbitals in decreasing order from higher energy to lower energy. So among these 4 orbitals, which got highest energy? Which got highest energy?
5F.
5F.
Very good, 5F. Okay. After 5F, which got highest energy?
6p, ma'am.
6p.
No doubt it is 6p. Superb. After 6p, we have confusion because both these orbitals got same n plus l value. If the orbitals with same n plus l value, then we have to decide by this principal quantum number. Which got higher number will have higher energy. So
It's 5p.
yes. So it is 5p and after which 4d. Is that clear? And actually, this is one of the neat questions. Okay. So if we are provided with the orbitals, then we have to know which got lower energy and which got higher energy. Basically, this is your half-pass principle, right? Okay. What is Hund's rule? What is Hund's rule? Whenever you're filling degenerate orbitals, what is degenerate orbital?
The successive orbitals.
Okay. Fine. Degenerate orbitals are nothing but orbitals with same energy. For example, I have 2s and I have 2p. Okay. First, which orbital we have to fill? Among 2s and 2p, which orbital we have to fill first?
2s, ma'am.
2s.
2s, right. We have no doubt in it, right. And after 2s, we'll be filling 2p. Suppose in 2p, we have 5 electrons or let us say we have 4 electrons. How to fill this 4 electrons? Generally, p subshell will have 3 orbitals, right? Actually, among 2s and 2p, 2s got lesser energy, which was very clear. We understood that from n plus l rule. But in 2p, we have 3 orbitals, right? But all the 3 orbitals will have same energy. And these 3 orbitals are considered to be degenerate orbitals. Whenever you're filling these degenerate orbitals, you have to fill orbitals. First, you have to half fill the orbitals and you have to completely fill that, right? So now I have 4 electrons and I have to fill 1 electron here, second electron here, third electron here, and fourth electron here. This is Hund's rule. Is that clear? We should not fill like this, which is wrong. Why? Why this is wrong and this is right? You would have studied about exchange energy, right? This configuration got more exchange energy, but this configuration got less exchange energy. The configuration with more exchange energy is more stable because what is exchange energy? Whenever you're filling degenerate orbitals, you have to fill the orbitals. First, you have to half fill the orbitals, right? Whenever you're half filling the orbitals, this electron and this electron will get exchanged. So electrons with same spin will get exchanged. Okay, this electron and this electron will get exchanged, and similarly this and this will get exchanged. Whenever there is an exchange of electrons of similar spin, there will be a particular amount of energy will get released out, and that energy is called exchange energy. If there is a lot of similar spin electrons, then there will be a lot of exchanges, and through which lot of exchange energy will be released out, due to which the stability of the atom will get increased. So because in this configuration we have lot of exchange energy released, that is why this configuration is more stable, and for this configuration exchange energy is less, so we should not go for this configuration. Am I clear? And that is Hund's rule. And Pauli's exclusion principle is nothing but no two electrons in an atom can have same set of quantum number. Okay, that is Pauli's exclusion principle. Fine. Next is electromagnetic radiation. You would have studied about electromagnetic radiation. So you have to know what is electromagnetic radiation, different types of electromagnetic radiation, and what is the basic difference between one electromagnetic radiation with another. And you have to know different wave parameters. What are all the wave parameters you have studied already? What are all the wave parameters you studied in electromagnetic radiation? Energy, wavelength, frequency, wave number, time period, right? These are all the wave parameters you should have studied in this electromagnetic radiation, and also you have to know the relationship between all those parameters. Okay, let us see the formulas and relationship between all those parameters. What is the formula which relates energy and frequency? Planck's formula, E is equal to,
H nu, ma'am.
very good, E is equal to h nu. So how energy and frequency are related?
They are directly proportional.
Yes, it is directly proportional. Very good. So E is equal to h nu. Okay, so energy and frequency were directly proportional. So here frequency can be expressed in terms of wavelength, right? What is the relationship between frequency and wavelength? Frequency is equal to C by lambda. So instead of frequency, I can write it as C by lambda. So how energy and wavelength are related? Energy is inversely proportional to wavelength. And how frequency and wavelength are related? They are inversely proportional. Frequency is inversely proportional to lambda, right? Okay. And what is wave number? Wave number is nothing but nu bar, and it is the reciprocal of wavelength, right? So this expression can also be written as E is equal to hc into 1 by lambda, and this 1 by lambda can be expressed as wave number, right? E is equal to h into c into nu bar. That's it. So how energy and wave number are related? Energy is directly proportional to wave number. So these are all the relationship between them, and we left one parameter, which is time period, right? What is time period? Time period is the reciprocal of frequency. That's it. And also you have to know the formulas for all these wave parameters. So for energy, what is, the unit. What is the unit of energy? We can express energy in terms of, yes, very good, very good. We can express energy in terms of joules, electron volts, calories, ergs, and all that, and we have seen the conversion between them. And what is the unit of wavelength? What is the unit of wavelength? Very good, it is meter. And what is the unit of wave number? What is the unit of wave number?
Verse, ma'am.
Meter inverse, yes, because wave number is the reciprocal of wavelength. And what is the unit of frequency?
It is hertz, ma'am.
Very good, hertz. Frequency can be expressed in hertz or in terms of second inverse, and there is no conversion between hertz and second inverse. 1 hertz is equal to 1 second inverse. So you need not worry about conversion and all that. And what is the unit of time period? What is time period? It is the reciprocal of frequency. And what is the unit of frequency? Second inverse. So what is the unit of time period then? Seconds. That's it. Okay. So we have done with this electromagnetic radiation also. And you would have studied about hydrogen spectrum, right? So in hydrogen spectrum, you guys would have studied only one formula. May I know the formula which you studied in a hydrogen spectrum? Or what are all the stuffs you studied in hydrogen spectrum?
Wave number is equal to 1 by lambda, which is equal to R into 1 by n1 square minus 1 by n2 square, ma'am.
Very good, Tatvatika. Yes. So there is only one formula on hydrogen spectrum. That is what Tatvatika told us now. Let me write the formula here, okay? So basically the formula is 1 by lambda, or 1 by lambda can be expressed as wave number, which is equal to R or RH into, she left one parameter. Actually, there should be a parameter called Z square into 1 by N1 square minus 1 by N2 square. But actually her formula was also right, because we are talking about hydrogen spectrum, right? And what is the atomic number of hydrogen? What is the atomic number of hydrogen? Basically, it is 1. So here Z value is 1. So in most of the books, the formula will be RH into 1 by N1 square minus 1 by N2 square. But we have to write this Z squared because if the question is like they're asking the wave number for helium ion, then we have to write the atomic number in the formula, right? If you didn't memorize this Z, then you will not know where to substitute the atomic number of helium. So memorize the formula like this. Okay, so basically this formula was derived from your Bohr's energy formula only, but you need not substitute all those energy values and all. You just memorize this and substitute the value of N1 and N2 from which you can calculate the wave number. Okay, but basically what is hydrogen spectrum? Apart from this formula, what are all the stuffs you studied in hydrogen spectrum? And basically what is this RH?
It is constant, ma'am.
Yes, it is Rydberg constant. And the value of Rydberg constant is 1.97 into 10 power 7 meter inverse. And this Rydberg constant is applicable for hydrogen and hydrogen-like system because this formula is derived from this formula was derived from Bohr's concept. And Bohr's model is applicable for hydrogen and hydrogen-like system. So similarly, Rydberg constant cannot be used for any other atom. We have to use this for hydrogen and only single electron systems. Okay, fine. You would have studied about different series, right? What are all the series you studied in hydrogen spectrum? Lyman series?
Lyman, Balmer, Patchen, Bracket, and Fun series.
Fun, and another one is Humray, right? That's it. And next topic you would have studied is Heisenberg's uncertainty principle. That is very famous principle. Can you please tell me what is that? Ajay? What is Heisenberg's uncertainty principle? Avantika?
Ma'am, the position and the velocity cannot be determined at the same time.
Of whose velocity and whose position cannot be measured simultaneously?
Ma'am, electron or minute or small size particles.
Yes. Electron or any microscopic particle. Okay, fine. Avantika was right. If any microscopic particle is moving with a particular speed, then we cannot measure the position and momentum of that microscopic particle simultaneously with accuracy. Okay, if we try to measure it simultaneously, then we'll end up with error. That is what Heisenberg's uncertainty principle is all about. In 11th standard syllabus, they are talking about only two physical parameters. One is position and another one is momentum. But there are different, we can have different physical parameters for that. But that is not in our syllabus now. So in our syllabus, they are talked about only position and momentum, right? So by using position and momentum, I can write the mathematical expression for Heisenberg's uncertainty principle, which is delta x. This is position, and change in momentum, which is small p, which is greater than or equal to h by 4 pi. This is the mathematical expression of Heisenberg's uncertainty principle. And this momentum can be expressed in terms of what is momentum? Here, the microscopic particle is moving linearly. So, the momentum associated with this particle is linear momentum. And what is the formula to calculate linear momentum? Mass into velocity, right? So, here this is change in momentum. So, for which you have to represent this momentum as m into delta v. See, here microscopic particle is moving, but moving microscopic particle will not have any change in mass. So delta is not applicable for mass. So delta is applicable only to velocity, because a moving particle's velocity may vary, but not the mass. Okay. So this can be written as delta x into mass into delta V, which is greater than or equal to h by 4 pi. Okay. Apart from this position, momentum, position, and velocity, we can have another two physical parameters, which is energy and time. Energy and time cannot, I mean, these two parameters cannot be measured simultaneously. Okay, so these are all the various mathematical expressions of Heisenberg's uncertainty principle. And sometimes you would have seen this parameter, which is called h cross. Basically, h cross is a symbol which represents h by 2 pi. Okay, that's it. So we can use this h cross here, like delta x into delta p, which is greater than or equal to h cross by 2. This is also fine. Okay, is that clear? And finally, you would have studied about this photoelectric effect. What is the formula you studied in photoelectric effect? There is only one formula for that, right? What is the formula related to photoelectric effect? There is only one formula. H nu is equal to? Is that Pratika?
H nu is equal to H nu naught plus half mv square, ma'am.
Very good, that's it. So basically, what is photoelectric effect?
Ma'am, when a photon is, suppose when we give a photon to a material like metal something, the energy from the metal ejects along with the kinetic energy, ma'am.
Okay, fine.
And kinetic energy is also given by it is also contributed mostly by the proton which we given.
Okay. Fine. Very good, Pratika. Okay, guys, listen. Let us take an atom of a metal. Okay. So, in an atom, at the center, we'll be having nucleus. Around this nucleus, we'll be having lot of energy levels. In this energy level, electrons will be present, right? Let us say third shell is the valency shell of this atom. Okay. In inner shells also we'll be having lot of electrons. So this valency electron will be bounded by this nucleus. Definitely all the electrons will get binded, but I'm talking about only this valence electron. Now what I have to do is I have to knock out this valence electron from this atom. So what I have to do, I have to supply a particular amount of energy on this electron, right? But to remove this electron, basically I have to know the binding energy between this nucleus and the electron, right? But we don't know how much energy is required to break this binding energy between nucleus and electron. So what we'll do, randomly we'll supply a particular amount of energy on this electron, but definitely more than the quantity, right? So this complete energy will be absorbed by this electron. Okay. In this complete energy, one part of the energy will be used to break the attraction between nucleus and the valence electron. Okay. So in h nu, one quantity of energy was used to break the attraction between the nucleus and the valence electron. And how about the rest of the energy? Definitely now electron came out of the atom, but electron got extra amount of energy. Now electron cannot stay there because electron got more amount of energy, and this electron has to dissipate its energy in any means, right? So this electron, what it will do? It will move with a particular velocity. So the energy associated with any moving particle is called kinetic energy, right? So the energy what I supplied on this electron was h nu, in which one part of the energy was used to break the binding energy, and another part of the energy was dissipated as kinetic energy. And this is the formula we are using in photoelectric effect. Why it is called photoelectric effect? The energy what I've used on this electron is photon, and this photon ejected an electron out from the atom, and that electron is called photoelectron. And whenever a charged particle is moving with a particular speed in a particular direction, then that leads to a current. So here photoelectron is the charged particle what I'm talking about, and this is moving in a particular direction. This leads to a current called photoelectric current, and this effect is called photoelectric effect. That's it. So here the formula what we're going to use is h nu, which is the incident energy, and this is the binding energy, and this is the kinetic energy. But binding energy can be represented as h nu naught, and kinetic energy can be represented as Tatratika told, it is half mv square. That's it. Okay, so this is called binding energy, or it can also be called as work function. Is that clear? Is that clear? Okay. Apart from these concepts, you would have studied about Strontius's equation, de Broglie's wavelength, and all that, right? Okay. Now we'll move on to questions. Shall we? Shall we move on to questions now? Fine. First question is, see, we have two columns. In first column, we have few species, and in second column, we have a few terms like isotopes, isotones, isodiphers, and isobars, and we have to match them. Okay. Basically, we know what are those, right? Isotopes are nothing but the chemical species with same atomic number but different mass number. And isotones are nothing but the species with same number of neutrons. And isobars are species with same mass number but different atomic number. And isodiphers are nothing but the species with same neutron excess. I think this isodifer is little new to you, I guess, right? I think isodifers are new to you, right? What is isodifer? If the two species got same number of neutron excess, then that is called isodifers. But how to calculate neutron excess? To calculate neutron excess, here is the formula. Mass number minus 2 into atomic number will give the neutron excess. If two species got same neutron excess, then that species were called isodifers. Okay. How to calculate number of neutrons? Basically, I'm asking how to calculate. What is the formula to calculate number of neutrons?
Mass number minus
Atomic number.
Very good. Very good. Mass number minus atomic number. That's it. Please match the following and let me know the answer. You need not find for all the 5 species. You just screen the options and tell me. What is the answer? Kana, what is the answer for this question? Okay, Tatvatika's answer was option A. How about rest of the students? Okay, see, first species seems to have same atomic number. Whenever you're writing any element, this will be the symbol of the element, and bottom of the element will have atomic number, and at the top we'll be writing the mass number, right? So here these species got same atomic number but different mass number, so this is considered to be isotope. And this fifth species were also same atomic number but different mass number, so this is also considered to be isotope. So first and fifth one will have A. So first and fifth one got A here and here also, right? And here also. So we cannot screen the option from isotopes. And how about isotone? we have to check for the species with same number of neutrons, right? So which got same number of neutrons? How about third one? 76 is the mass number, 32 is the atomic number. So 76 minus 32 is 76 minus 32 is
44, ma'am.
yes, exactly. It is 44. So this got 44 neutrons. How about this one?
44, ma'am.
Again, this is 44. So third one is a isotone. So 3 is connected with B. So definitely option 1. That's it. Okay. Check for these species. This will have same neutron excess, and here's the formula to calculate neutron excess. That's it. And this seems to be same mass number but different atomic number. So this is isobar actually. That's it. So shall we move on to next question? Okay, here is the next question. The E by M ratio is maximum for which of the following species? Here E represents charge and M represents mass. So we have to find the charge by mass ratio of all the species, and we have to check which got maximum value. So basically, what is the logic? To have maximum value, charge should be maximum or more, and mass of the species should be less, right? See, second and fourth option got helium. In fact, this helium's mass is very much greater than your hydrogen's mass and deuterium's mass. What is the mass of helium?
4, ma'am.
Very good, it is 4. Though the charge on this helium is 2, mass is very much greater than hydrogen and deuterium. Definitely, second and fourth option will not be our answer. So, how about first and third option? Which will have maximum charge by mass ratio? Though first and third option got same charge, but they are different in mass. Which got lesser mass and which got higher mass? Yes, Ajay? Hydrogen got less mass because as far as hydrogen is concerned, we'll be having one electron and one proton, and there will not be any neutron. As far as helium plus is concerned, there is no electron also. As far as deuterium is concerned, number of electron is 1, number of proton is 1, and number of neutron is also 1. According to this species, there is no electron here. So here, mass of this deuterium is due to both proton and neutron. Here, mass of the hydrogen is due to only proton. So which got lesser mass? Which got lesser mass among deuterium and hydrogen? Yes, it is hydrogen. So this got lesser mass. So this got maximum E by M ratio. Is that clear? Shall we move on to next question?
Yes, ma'am.
Fine. So here they're asking us to calculate the radius ratio of Bohr's orbit. So they're asking us to find the first 3 radius ratio of Bohr's orbit. Okay, we'll check that, Ritika. Kundabalarisi, what is your answer, Kanna? Avantika? Daniel Lakshmi? Third option. Okay, we'll check. So first we have to know the formula to calculate the radius. So what is the formula? Rn is equal to 0.529 n square divided by Z angstrom. And they're asking us to find first 3 radius. So which means R1 is to R2 is to R3. So R1 is 0.529. Yes, it is. So here n value is 1. So 1 square divided by Z Here 0.529, here the n value is 2, so 2 square divided by z. And here 0.529, 3 square divided by z. So all the common terms will get cancelled out. So 1 is 2, 2 square is 4, and 3 square is 9. So answer is option C. Right. So all the students were right. So shall we move on to next question? So here they have given lithium 2 plus ion, and they are asking us to find the ratio of R2 and R5, which is very easy. R2 and R5.
Second option.
Okay. Ajay's answer is second option. How about Marimuthu? Okay, Daniel Lakshmi's answer is option 2. Marimuthu's answer is also option 2. Okay. We'll check that. So here, this is R2. So 0.529 n square divided by Z is the formula. So 0.529, value of n is 2. So 2 square is 4 divided by, this is lithium. Atomic number of lithium is 3. This to 0.529. Here, the shell in which electron is present is 5. So 5 square, that is 25 divided by 3. So 4 is to 25 is the answer. So answer is option 2. Okay, shall we move on to next question? The energy of hydrogen atom in nth orbit is En. Then energy in the nth orbit of singly ionized helium ion will be dash. The energy of hydrogen atom in nth orbit is En. Then energy in nth orbit of singly ionized helium ion will be dash. Okay, Tatvatika's answer is option 1. We'll check. So, formula to calculate energy is minus 13.6 Z square divided by N square, right? According to this hydrogen atom, the atomic number is 1. So, 1 square divided by, they are talking about nth shell. So, it is N square, angstrom. So, they are representing this as En. So, En is what? Minus 13.6 divided by N square. But they're asking the question for singly ionized helium. What is singly ionized helium ion? That is helium plus. So for this, the energy is En prime. To differentiate the energy of hydrogen and helium, I'm writing it as En prime, which is equal to minus 13.6. What is the atomic number of helium? It is 2. So 2 square is basically 4 divided by the energy level they are talking about is again nth shell. So it is n square. So minus 13.6 divided by n square is En. So En prime is nothing but 4 times of En. So answer is option 1. That's it. Next question. Okay, the graphical representation of energy of electron and atomic number is dash. Very good, Avantika. Okay, next question. The graphical representation of energy of electron and atomic number is dash. Okay, Avantika's answer is option A. Tatvatika's answer is also option A. So what that option A implies, as atomic number increases, energy is also getting increased, right? But that is not true actually. You just write the formula and check. You know the formula to calculate the energy of the electron, right? You just substitute the value or you just increase the value of Z. Now Avantika's answer is right. It is actually option 4. Finally, check. What is the formula? E is equal to minus 13.6 Z square divided by N square electron volt. So here atomic number and energy were seems to be directly proportional, right? But if you increase the value of Z, energy's value will get increased. There is no doubt in it. But what is the sign here? We have negative sign. So as you increase the value of Z, the quantity will get decreased. So the energy will get decreased. So fourth option is the right answer. As the atomic number increases, energy is getting decreased linearly. Okay. Is that clear? Fine. Okay. How about N? If you increase the value of N, what will happen to the energy? If you increase the value of N, then what will happen to the energy of the electron?
It will decrease.
Okay, Ajay's answer is energy will get decreased. Let us see. For example, I have hydrogen atom in which I have only one electron. Here, the electron is present in first shell. So, what is the energy? E1 is equal to minus 13.6. Since I'm talking about hydrogen atom, the atomic number is 1. So, 1 square divided by 1 square, which is just minus 13.6 electron volt. Okay. In second case, the one electron which I'm talking about is present in second shell. Okay, so what is the energy of the electron which is present in second shell? E2 is equal to minus 13.6. Here also I'm talking about hydrogen atom only. So N is equal to, the atomic number is 1. So 1 square divided by, what is the, in which shell the electron is present? In second shell. So 2 square is 4. So minus 13.6 divided by 4 is minus 3.4 electron volt, right? So as the N value increases, what is happening to its energy?
I'm increasing, ma'am.
Yes, it is increasing, right? So if you increase the value of N, or if the electron is moving, it is moving away from the nucleus, the energy is getting increased. Okay, fine. Let us move on to the next question. The energy required to remove an electron from mth shell of hydrogen atom is 1.51 electron volt. Okay. Then the energy of first excited state will be dash. If the electron is present in mth shell, then I have to supply 1.51 electron volt. Okay. But the question is, now the electron is present in first excited state, and what is the energy of that electron? You need not get confused by this statement. You just answer for this question alone. They're asking for the energy, and the shell they're talking about is first excited state. So you have to know the value of N for first excited state. That's it. Tony's answer is option 3. Okay. So what is the value of N for first excited state? Ground state is 1. For first excited state, it is 2. So just now we have calculated the energy of the electron if it is present in second shell, right? It is minus 3.4 electron volt. So answer is option 3. Is that clear? Shall we move on to next question? Okay. How about this question? This is also very easy. The ionization potential of the hydrogen atom is 13.6 electron volt. The energy needed to ionize a hydrogen atom, which is in its second excited state, is about dash. They're asking us to calculate the energy to ionize the hydrogen atom if the electron is present in second excited state. Tatvatika's answer is option 4. Okay. So, see guys, I just want to make one point clear here. They are talking about two things. One is the energy of the electron, and second one is ionization energy. In some point they were similar, but in some point they are different. Okay, let us see the similarity and differences between them. For example, this is hydrogen atom. So this is basically a nucleus. This is the first shell in which electron is present. Okay. We are calculating the energy of this electron. Basically, this is hydrogen atom. So the energy of this electron, since it is present in first shell, the energy of this electron is minus 13.6 electron volt. So whenever you are expressing the energy of the electron, then express with negative sign. Okay, this is the energy of the electron. Now I have to remove this electron from the atom. Now I have to knock out this electron from this atom. So for which I have to supply a particular amount of energy on this electron, right? So the amount of energy you're supplying on this electron must be expressed in terms of must be expressed in positive sign. Okay, how much energy you should supply? How much energy of this? I mean, what is the energy of the electron? That same amount of energy you have to supply on this electron. So the energy of this electron is minus 13.6, and the same quantity you have to supply on this electron. So plus 13.6 is the ionization energy. Okay, so energy of the electron you have to express it with negative sign, and ionization energy you have to express it in positive sign, because ionization energy is the energy you're supplying on the atom. Okay, you have to express with positive sign. Is that clear? So similarity is the quantity, but the difference is their sign. So energy of the electron must be expressed in terms of in negative sign, and ionization energy should be with positive sign, right? So here they are talking about second excited state. So ground state is n is equal to 1. First excited state is n is equal to 2. And second excited state is n is equal to 3. So for n is equal to 3, you have to calculate the energy, which is minus 1.51, and they are talking about ionization energy. So I have to express it with positive sign. So answer is option D, and Tatvatika was right. Is that clear? Shall we move on to next question? Okay. This question is basically from hydrogen spectrum. They're asking us to calculate the ratio of minimum frequency of Lyman and Balmer series will be dash. They're asking us to calculate the ratio of minimum frequency of Lyman and Balmer series. I'll give you 60 seconds. You just calculate and please let me know. Or you just tell me how to do that. So you would have learned only one formula in this hydrogen spectrum, which is related to wave number, right? So you have to convert this wave number into frequency, and you have to check which got minimum frequency of Lyman and Balmer, and you have to divide those to get the answer. Are you guys doing it? If you guys finding it difficult, you just let me know. We'll do it together. Shall we do it together? Shall we?
Yes, ma'am.
Okay. Okay. So what is the formula we learned in hydrogen spectrum? 1 by lambda, which is wave number, which is equal to Rydberg constant into Z square into 1 by N1 square minus 1 by N2 square. This is the only formula we know from hydrogen spectrum. Here they are talking about frequency, but the formula is completely related to wave number. Now I have to convert this wave number into frequency. How to do that? We know the relationship. nu is equal to c by lambda, right? So what is nu? C into 1 by lambda. So I have to multiply the c with 1 by lambda. Basically, what is c? It is velocity of light, which is 3 into 10 power 8 meter per second. So I have to multiply velocity of light with wave number to get frequency. So in left and right, I'm multiplying it with c. So c by lambda is equal to c into Rydberg constant into z square into 1 by n1 square minus 1 by n2 square. Okay, so what is c by lambda? We know it is nu. So nu, which is frequency, is equal to velocity of light, Rydberg constant, z square into 1 by n1 square minus 1 by n2 square. So this is the formula we're going to use here. Fine. So they're asking us to calculate the minimum frequency. So what are all the Lyman series transitions? So basically, if the electron is present in excited state, it can come back to the first energy level, which is n is equal to 1. That is the Lyman series is all about. So from excited state to electron can come to first energy level. So excited state can be second state to first state, third state to first state, fourth to first state, fifth to first state, or infinity to first state. These were all of Lyman series, right? But they are talking about minimum frequency. What is minimum frequency? That is the minimum energy transition. Among these transitions, which is minimum energy transition? Which is minimum energy transition? See, this is first state. Okay, this is second state. This is third state. This is fourth state. This is fifth state. This is sixth state. Okay. Electron can come from second state, or electron can come from third state. Electron can come from fourth state. Electron can come from fifth state. Among these transitions, which transition got lesser amount of energy, which got lesser energy gap between second and first transition, right? So this transition got lesser energy, this transition got lesser frequency, because we know energy and frequency were directly proportional. And how about wavelength? This got maximum wavelength, but here they are talking about just frequency. So second to first transition got minimum frequency. So here n2 of Lyman series is 2 and n1 is 1. Okay, this is for Lyman series. How about Balmer series? In Balmer series, electron from the excited state will come back to the second shell. So the excited state can be from third state to second state, fourth state to second state, fifth state to second state, or infinity to second state. Among these transitions, which transition got minimum frequency?
Ma'am, 3, ma'am.
Very good. 3 to 2. So here n2 value is 3 and n1 value is 2. You just have to substitute those values here. So for Lyman series, you'll be having one formula, and for Balmer series, you write another formula and substitute the value of n1 and n2, and you just divide those and let me know the answer for this question. So every common term will get cancelled out. So you just simplify and let me know the answer. So what is the answer? You need not substitute the value of C, Rydberg constant, atomic number, and all that. Anyway, that will get cancelled out. You just substitute the value of N1 and N2 in both the series and divide those. Okay. Marimuthu answer was option A. Okay, we'll see Marimuthu. Jay Shakti, Ajay, Avantika, Tatratika, Pundamalarasi, Tony. Are you guys doing it? Okay, Avantika's answer is option C. So I got two different answers. One is option A, and another one is option C. Ajay, what is your answer, Kana?
Option 3.
Okay, Jay Shakti's answer is option 3. Ajay's answer is option 2. Okay, fine. So I got three different answers. Okay, shall we do it together then? So what is the formula? So seems to be option C. We'll see. Okay. So frequency of Lyman series, which is equal to C into Rydberg constant into atomic number into 1 by n1 square. So according to Lyman series, what is the value of n1? It is 1. Minus what is the value of n2? It is 2. So 2 square is 4, right? And how about Balmer? Frequency of, velocity of light, Rydberg constant, atomic number divided by. So according to Balmer series, n1 value is 2. So 2 square is 4 minus 1 by n2 value is 3. So it is 9. Okay. So we have to simplify those formulas. So C into Rydberg constant atomic number here 1 minus 1 by 4. So what is that? 1 minus 1 by 4 is
3 by 4.
3 by 4. That's it. Here frequency of Balmer series, which is equal to C into Rydberg constant into atomic number divided by, here it was 1 by 4 and minus 1 by 9. You just cross multiply this. So 9 minus 4 divided by 36.
5 by 36.
Yes, 5 by 36. That's it. So you have to divide these two. So these two terms will get cancelled out. So 3 by 4 into 36 by 5. So what is the answer?
27 by 5.
Okay. Yes, 27 by 5. What is 27 by 5? The answer was not in fraction. So 27 by 5 is
5.4.
5.4. So answer is option C. Is that clear?
Yes, ma'am.
Okay, Kana. We'll move on to the next question. This is a similar type of question, but there is a very small difference here. The ratio of minimum wavelength of Lyman and Balmer series. So here they are talking about wavelength, and here they are asking us to find the ratio of minimum wavelength. So first you have to have the formula which got wavelength, and you have to find the minimum wavelength of Lyman and Balmer, and you have to divide both, and you just want to come up with the answer. I'll give you 1 minute or 2 minutes. You just calculate and let me know. Tatvatika's answer is option 2.
0.25.
Okay. That is also option 2. Kanna, you have to tell me 0.25. Okay, it is not 25, 0.25.
Yes, ma'am.
Okay. So Tatvatika's answer and Jay Shakti's answer is
Ma'am,
option 2.
0.25.
Yes, it is 0.25. Yes. If you guys have any doubt, then I'll calculate here or we'll move on to next question. Shall we move on to next question? The right answer is 0.25. Okay. Avantika, do you have any doubt?
Ma'am, it is 4 by 3 RH into 5 RH by 36, no, ma'am.
It is not 4 by 3 RH.
Ma'am, wavelength means it should be inverse of the 3 RH by 4 for first line.
Yes, it is. Okay. Shall we calculate together?
Yes, ma'am.
Okay. So basically, what is the formula? 1 by lambda is equal to Rydberg constant into atomic number into 1 by n1 square minus 1 by n2 square. Right. First, we'll calculate for 1 by lambda, after which we can take reciprocal of that. Okay. So now we'll talk about this Lyman series. So 1 by lambda L, which is equal to Rydberg constant into atomic number into, we have to know the value of N1 and N2. They're talking about minimum wavelength, which means maximum energy. So which transition will have maximum energy? Infinity to first state, right? So here N2 value is infinity and N1 value is 1. So 1 by 1 minus 1 by infinity. So 1 by infinity is 0. So 1 by lambda L is RH Z square into 1. That's it. So this is equation 1. Another one is Balmer series. So 1 by lambda B, which is equal to Rydberg constant into atomic number divided by what is the minimum wavelength, which is the maximum energy from infinity to second state, right? So here 1 by 2 square is 4 minus 1 by infinity is again 0, right? So we have to divide this and this. You just divide and tell me what is lambda L, which is equal to 1 by RH Z square, right? And what is lambda B, which is 4 by RH Z square, right? You have to divide those. What is it, Kana? 1 by RH Z square into RH Z square divided by 4, right? These terms will get cancelled out. So the answer is 1 by 4, which is 0.25. So answer is option 2. Is that clear? Okay,
Yes, ma'am.
fine. So we'll move on to next question. And Poondamal Arasi also told 0.25, it seems. Very good, Kana. We'll move on to next question now. Okay. Here the question is from Heisenberg's uncertainty principle. Okay, let us see how to do this, and after this we'll wind up the session. Okay, they're asking us to calculate the uncertainty in position, which means they're asking us to calculate delta x of an electron whose mass is given in gram, but you can use it in kilogram also. So what is the mass of electron in terms of kilogram? It is basically 9.1 into 10 power minus 31 kilogram, and it is moving with the velocity of 3 into 10 power 4 centimeter per second. Okay, but you just convert this into meter. Okay, and finally you convert into centimeter. That is how you can minimize the error. Okay, and if the uncertainty in velocity is 0.011%. Okay, let us see how to do this. So they're asking us to calculate the uncertainty in position. So what is the formula? Delta x into, they are talking about velocity. So instead of momentum, I can write it as mass into delta v, which is equal to h by 4 pi. So they are asking us to calculate delta x. So delta x is equal to h by 4 pi into 1 by mass into change in velocity. So we know the value of h, which is 6.626 into 10 to the power of minus 34. Please use it in terms of kilogram. Kilogram meter squared second power minus 1, because denominator we have mass, and mass of an electron can be expressed in kilogram, so that we can cancel those kilograms. So don't use joule here. Divided by 4 into what is the value of pi? It is 3.14. And what is the what is the value of mass? It is 9.1 into 10 power minus 31 kilogram. And we have to substitute delta V. Delta V is nothing but we have to multiply the velocity and its uncertainty. So what is the velocity? 3 into 10 power 4. I asked you to write in meter, right? So what is the value of centi? It is 10 power minus 2 meter second inverse into what is its uncertainty? It is 0.011%. So divided by 100. I'm just substituting all those value instead of delta V here. So 3 into 10 power 4 into 10 power minus 2 meter per second into 0.011 divided by 100. Denominator I am taking to numerator. So I'm going to cancel the common terms. Kilogram will get cancelled out. 1 meter and meter will get cancelled out. Second inverse will get cancelled out. So we have only one unit, which is meter. So simplify all this and express that in centimeter. That will be the answer. Okay. So 6.626 can be written as 6.6 into 10 power minus 34. And 100 can be written as 10 power 2 divided by 4 into 3.14. 9.1 can be written as 9 and 3. That's it. And you just simplify all those 10 powers and finally come up with the answer. Okay. Please take this question as activity. Okay. Solve and you just post your solution in group. I'll check there. Okay. Is that clear? So in next class also we'll be solving questions from atomic structure. Okay. After which we'll move on to next chapter. Till now, you guys, do you have any doubt? So in next class we'll be discussing 20 more questions, and after which we'll be moving on to next chapter. Okay. Till now, do you have any doubt?
Ma'am, can you explain the exchange energy once more, ma'am?
Exchange energy. Okay, Kana. Give me a minute. I'll change the slide. Is the screen visible, Tatvatika?
Yes, ma'am.
Okay. For example, I have a D5 configuration. Okay. For example, I have 5 electrons in D subshell. Generally, what will be your arrangement? In D subshell, I'll be having 5 orbitals, and each orbital will have 1 electron. Right? This should be the right configuration. And we should not have the arrangement like this, right? So basically we'll see how this is right and this is not. Exchange energy is nothing but amount of energy released during exchange of electrons of similar spin. Okay, here this electron can exchange with this electron. This electron can exchange with this electron. This electron can exchange with this electron. This can exchange with this one. Similarly, this can exchange and this can exchange, this can exchange. Here, there are a lot of combinations possible. Okay. So, whenever exchanges are done, there a particular amount of energy is released, which is called exchange energy. If the exchange energy is more, then stability is more. So we can calculate the exchange energy of this configuration and this configuration as well. Here, this electron and this electron will get exchanged, and this electron and this electron will get exchanged. Here, this anti-clockwise spinning electrons can exchange. Yes.
Ma'am, here all are degenerate orbitals, ma'am. The orbitals have the same energy. So why should the energy be released, ma'am?
Okay, actually, they are all of same energy. There is no doubt in it. Whenever they are present, though they are present in the same energy level, see, since they are of same energies, only exchange is possible. If the electron is present in lower energy and if the other electron is present in higher energy, exchange is not possible there. For example, if I have 2s electron and I have 2p electron. Here I have 2 electrons, here I have 3 electrons. These 2 electrons cannot exchange because this energy and this energies are different. Okay, so 2s energy is lesser than 2p's energy. So exchange is not possible here. Exchange is possible within the degenerate orbitals. And you're asking me why it should exchange. Uh, because of this exchange, these electrons are releasing energy. Whenever the atom is releasing energy, basically the atom's stability is getting increased. So atom is finding every possible way to increase the stability, and exchange energy is one of the ways. Is that clear, Avantika?
Yes, ma'am.
Fine. So here, let us calculate the exchange energy. Okay. Here we can do it by combination, or I'm going to give you a shortcut. Okay. So here I have clockwise electrons. How many clockwise electrons are there? 5, right? So from 5 reduce 1. So 4 plus from 4 reduce 1 number 3. So from 3 reduce 1 number 2. From 2 reduce 1 number 1. That's it. You just add all these numbers. 5 plus 3 is 7. 7 plus 3 is 10. So 10 exchange energy, 10 unit of exchange energy. And basically exchange energy is the amount of energy released. So here this is minus 10E. This is the exchange energy of this arrangement. Okay. So similarly, we can calculate the exchange energy of this arrangement. Here clockwise spinning, I have 3 electrons. So from 3 reduce 1. So it is 2. So from 2 reduce 1. 1. So 2 plus 1 is 3 exchange energy. So since exchange energy is the amount of energy released, this has to be expressed in terms of a negative sign. That's it. And clockwise spinning, anti-clockwise spinning, I have 2 electrons, and from 2 reduce 1. So only 1 exchange energy is here. So by adding these two, minus 4 is the exchange energy of this configuration. So both the system got only 5 electrons. And among these two configurations, which got higher exchange energy? Here, because here 10 unit of energy was released. Here just 4 unit of energy was released. Whenever atom is releasing more amount of energy, its stability is getting increased. Tatvatika, is that clear, Kana?
Yes, ma'am.
That's it. Is there any other doubt?
No, like orbitals and subshell are same, ma'am.
No, they are two different terms. See, shell is nothing but K, L, M, and all that. Okay, for K, N values 1. Each shell will have subshells, which is S, P, D, F. They are subshells. And each subshells will have sub-subshells, and they are called orbitals. Okay, so
Okay.
each shell, inside each shell, there will be a subshell, and each subshell there will be sub-subshell, And subshell is also called as orbital. And subshell and orbital were not same. They are two different terms.
Thank you, ma'am.
Okay, Kama. Any other doubt? Fine. Shall we wind up the session? Okay, Kana. In next class also, we'll be discussing questions from atomic structure. So please revise all those concepts and formulas related to that. Okay? Fine. Bye-bye. Good night.
Thank you, ma'am.
Thank you, ma'am.